Welcome everyone to our March Science by the Glass. We are really delighted to feature our colleague, Jason Furtado from Oklahoma. We here at Texas Tech are part of the South Central Climate Adaptation Science Center, which includes University of Oklahoma, Oklahoma State University, New Mexico State, and Texas Tech, as well as Louisiana State. So we are delighted to be able to feature many of our partners in these Science by the Glass events. So not only that, but Jason is an expert in the topic that is on everybody's mind today, which is climate change and weird weather. What's up? This is literally what he studies. And he has come to us through a sort of a zigzag route. He started off studying in Vermont. Is that right, Jason? Then went to Colorado, then went over to Georgia, now went down to Texas. So if you go anywhere, I think the only place you could go after this is potentially Miami, the Florida Keys, or Puerto Rico to continue the pattern. But what he studies is the intersection between weather and climate. So weather is what happens over short time scales. Climate is what happens over at least 20 to 30 years. It's the average statistics of weather over that time. And Jason studies right at the intersection of those two events, looking at how weather influences climate and how climate influences weather. Jason is also a trivia champion. I just learned, and I did not know this before, that he is part of a trivia team that came second in their statewide championship in Oklahoma, and they actually went to the national trivia finals. So I don't know if you want to sort of take advantage of that in the Q&A and see if you can stump him with a few trivia questions too. But you can certainly ask questions as you go along in the Q&A. It's open at the bottom of your Zoom screen if you're listening on Zoom. If you're listening on Facebook, you can put your questions in the comments under our post, and Mackenzie and Randallin are monitoring the comments. They'll be able to add them to our Q&A on Zoom, and you can put those questions in at any time as you listen to Jason, anytime in the next half hour. And then when Jason's done, he'll be doing a live Q&A, taking your questions, co-hosted by John Zach, who also directs our Climate Center here at Texas Tech. So if you have any questions that go along, please go ahead and put them in the Q&A. Look over in the chat for links to learn more about Jason Furtado's research. He has a website there. We also have links in the chat with important information about our next events, including our event coming up in a couple of weeks, which is talking to Bill McKibben about his latest book called Falter. But for now, thank you, Jason. Welcome, and take us away.
All right. Well, thank you so much, Catherine, for that introduction. Kind of a funny thing is, when we went through our trivia, never really got any weather or climate topics that I could really, capitalize on, but we still did pretty good. So thank you so much again for having me here. I'm really excited to talk about this, and especially because of recent happenings here in the Southern Plains. But the talk that I'm going to be discussing today is going to be extreme winter weather in the midst of an overall warming world. And so, before I get into this, some of the results that I'll show are actually part of a whole collaboration. Science is collaborative. And these are just some of the colleagues, some of my students, and also fellow colleagues that have helped me to put together these results. So Bailey Jarrett, Carly Narotsky, Ollie Millen, Matthew Barlow at the University of Massachusetts in Lowell, and then Judah Cohen at AER Verisk Analytics. Also, this wouldn't be possible without funding from the National Science Foundation and also NOAA. And you can also find out more about my group in the link. There's a link in the chat to my website where you can find out more information about that. So let's take a look. And let's just start with the overview. Our world is warming, and we know this. We know that increases in greenhouse gases in our atmosphere are causing the globe to warm. And so this animation was created by NASA, and it's an animation from the late 19th century until near present about the changes in temperature across the globe. And what I like about this is because usually we just take a look at one value over the whole globe. The globe has warmed 1 degree Celsius, let's say. But this actually tells us that the warming pattern is actually very different depending on where you live. And so as you'll see in the movie, as we start to get more and more reds and oranges, meaning the planet is getting warmer with time, you can see that areas, especially in the northern hemisphere, are increasingly become warmer much faster than, say, areas here in the tropical belt. And so you can see that very well towards the end of this loop over here, where you see lots of reds in the northern hemisphere versus in the tropics. So we're getting warmer. But it's not equal everywhere. And so I want to highlight this a little bit more by now zooming in. And now we were looking at that sort of on these annual timescales. I'd like to zoom in particularly into the winter months, because that's when some of the really interesting stuff has been happening. So I've sort of taken a little bit of a snapshot here. These are wintertime trends in surface air temperatures starting in about 1960 until 2018, so just about a couple of years ago. And so that's what's plotted here in this map. And you can see that most of the map is, of course, red and orange, which is positive, meaning that we're having a positive trend. This is the rate of change with time. On the left is sort of taking the average of all these numbers at each latitude and showing you that indeed, that as we go poleward or towards the North Pole, that trend is increasing. So in other words, the magnitude of the rate of change of temperature is becoming more the further north that you go. So this is overall the temperature trend that's been happening since 1960. But something interesting actually happens when you look even closer in. So if we go now within about the last 30 years and we do the same analysis within the last 30 years, that's the map that we get. And you can see, if you look quickly, you can still see the big reds that are going on in the Arctic. I'm going to talk more about that because that's a key player in this. But I also want to point you out to these other areas that are going on here over the continent, say over Asia, and also over parts of North America, where you can see that the colors here are actually white, which means almost a neutral trend, or blue, which means actually that temperatures have been cooling with time from 1990 to near present. So in other words, winters have actually, since 1990, have gotten slightly cooler than they were. So today, the winters are actually a little bit cooler than they were in 1990. Now, overall, we're still warmer than we were 60, 70 years ago. But this recent trend is kind of interesting because, again, I just showed you a map where the entire globe is warming. So how can it be that certain areas are actually starting to experience slightly colder winters over the last 30 years? And in particular, if we go ahead and we zoom in here onto the southern plains, we can see that, in fact, since 1990, the overall trend in our wintertime average temperature is about zero. I mean, you can see that there's been a lot of warm winters, which is the up part, cold winters, which are these down or dip areas. But overall, the overall trend is almost zero. So over the last 30 years, our winters have actually not gotten warmer. They've actually gotten a little bit more variable, lots of ups and downs. Well, this is also reflected if we look at cold air outbreaks. And so this is some work that I've been looking at in terms of what is the frequency of cold air outbreaks that are hitting the plains over the last few decades. And so you can see that for sure during the 1950s and the 1960s, we had, roughly about 15 to 20 cold air outbreaks per decade. That went down a little bit, but again, since the 1990s, we're seeing an increased number of cold air outbreaks that are happening every decade across the plains. So again, there's been this trend that we're getting some more colder and, of course, more extreme weather, as I'll discuss in a second. And of course, we can't talk about this without talking about the recent really big cold blast that came through towards the middle of February. So this is a map taken on Monday, February 15th, pretty much during the heart of that cold wave. And you can see that across the central part of the United States, we have temperatures. These are departures from the average. We have temperatures that are almost 30 degrees Celsius below what they should be for this time of year on that date. We're talking about departures that were almost 45 to 50 degrees Fahrenheit in some of these places. So extreme cold. And actually, in terms of the departure from the average, here in the central United States, we had the coldest departure from averages than anywhere across the entire globe. So super extreme weather going on here. And that led, of course, to a lot of impacts across the southern plains, where we had, of course, a lot of issues with power, a lot of issues with water, snow, and then, of course, infrastructure. All these things were caused by this extreme blast of cold and also snow and ice that came across this area. So these are sort of telling you that, our winters over the last 30 years have been getting a little bit more extreme and a little bit colder. Now, it's not just restricted, of course, to the southern plains. If we look at elsewhere across the United States, we're also seeing some of these kind of signals of extreme weather. So as an example, what I'm showing here are the top 10 snowstorms for every big city in the Northeast. And so that's what all the dots are. You go through the record, you count up what their top 10, the most snow that's fallen in a day, what are the top 10, and you plot them out as a function of time. And you can see since 1880, records go back to the late 19th century. Since 1880, look at the cluster of dots that have been happening all towards the end of the period, meaning most of the top 10 snowstorms in the Northeast, in terms of total amount of snow that have fallen, have actually occurred not way back in the past, but actually over the last 30 years. So again, this is another example of extreme winter weather that's occurring in the middle of an overall warming planet. So we kind of have this conundrum now. On the one hand, we have the globe and we have global climate change. Temperatures are getting warmer with time. But on the other hand, we're experiencing these major bouts, these sort of big bouts of really extreme, short-term, but very extreme cold and snowy winter weather. And so the question is, how do these two things kind of go together? How do you get a planet that's warming and still have these major extreme cold air outbreaks? And so this has sort of been the crux of some of the work that I've been working on and others, trying to understand what seems like a paradox, but actually may not exactly be, as I'll show you. So again, I want to bring back, this is now a still image of that movie that I showed you, kind of paused at the end here. So this has been the last 5 years in terms of our temperature change that has happened since the 19th century. And again, when you look at this map, you can see that the biggest changes have happened over the far northern hemisphere across the Arctic. The rate of change there, as I've mentioned, has been almost twice as much as what's happened across the tropical belt. And this is what we call Arctic amplification. This is a process by which the Arctic regions are warming at a much faster rate than the tropics. Now, the Arctic is still cold. This isn't the actual temperature, right? The Arctic is still cold. It's still very cold at the North Pole, and it's still warm in the tropics. But that change in temperature is happening the change is happening much larger in the Arctic than it is in the tropics. And this is having a lot of different this is being caused by, but also causing other major changes in our climate system. Probably the most iconic change that has happened due to Arctic amplification has been the loss of Arctic sea ice. And so this is a movie from 1979 showing the minimum area, so the lowest size that the total Arctic is covered with sea ice. And you can see with time that that number is decreasing. And in fact, since the middle 1990s, there's almost been falling off a cliff in terms of sea ice. Now, this is both caused by Arctic amplification as the temperatures warm, but this is also what we call reinforcing Arctic amplification, because as we start losing more and more sea ice and also snow cover at the higher latitudes, that we're allowing now more sunlight to be absorbed into the higher latitudes. And if there's more sun that can come in, that's going to cause the temperature to go up. Well, if the temperature goes up, then that means that as the air gets warmer, more ice is going to start depleting. As more ice starts depleting, the temperature goes up further, more sun is able to get in, temperature goes up. We start this whole cycle going on that's going to cause that rate to really be much higher than it is outside of the Arctic. So this is what's happening within the Arctic, but sort of to paraphrase a popular saying, what happens in the Arctic doesn't always stay in the Arctic. So this is sort of a flow chart to give you an idea of sort of how these things can all come together. So on the left here is the Arctic amplification that I was just talking about. And that can cause, of course, changes in Arctic sea ice, in Eurasian snow cover. So those things can happen within the Arctic, but now outside of the Arctic, that can also start to change other features, including the jet stream. So the jet stream is a river of air in our atmosphere. It's where the storms like to travel along. And so the jet stream typically goes through the middle latitudes, and it can be, sometimes it could be straight east-west, or it could form big dips and big ups and downs that can cause storms, or that can cause sunny weather, depending on where it is. But Arctic amplification can also affect that type of jet stream as well, because one of the controls of the jet stream is actually that temperature difference that's happening between the Arctic and the middle latitudes. So if the Arctic is getting really warm faster than the lower latitudes, then that difference between the two is going to start to decrease. And that's going to cause the jet stream to start to lose a little bit of its punch. Once you start losing the punch, it's sort of like we've taken a rope that was really sort of tight on, and we've loosened it. So now the rope is a little bit more, you get more slack in it, and you can cause a little bit more of the waves and these big meanders that can start to happen. Now, the other big thing on here that I want to talk about is the polar vortex. And this has been now in the news so much, it's sort of gotten a life of its own. If it's not a Godzilla El Nino, it's a polar vortex attack that's happening. But really the polar vortex, let me present a little bit sort of what the polar vortex is. It's not something that's happened because of climate change. It's something that's in our climate system all the time, but it can be affected by climate change. So what is the polar vortex? Well, the polar vortex is a big pool of cold air that's in the Arctic, and it forms during the winter months. Now, as this cold air starts to pool in the Arctic, it's not only happening at the low levels, but also at the upper levels. And a lot of times when we talk about the polar vortex, we're talking about circulations within the stratosphere. Stratosphere is the layer above where we are. So the layer we live in is the troposphere, where our weather happens. Above there is the stratosphere. Really important because that's where the ozone layer is. But in terms of this topic, it's also where the polar vortex is as well. And so when the polar vortex, if you get cold air, polar vortex tends to form. It then starts to form a circulation, a westerly circulation around it. It's an area of low pressure. So in this picture, what I like about this picture is it actually depicts it as a 3D structure, but also as like a bowl. And so you can imagine this circulation going through in this 3D structure. Well, when that's happening and it's a strong and stable polar vortex, that's going to sort of keep all of the cold air locked up there in the Arctic. Now, when the polar vortex gets disrupted, and the way it gets disrupted is actually can get disrupted from below through intrusions of heat that are happening from the lower latitudes to sort of mix up the air and make it less cold. When that gets disrupted, then that's sort of like the ice skater that sort of takes their arms and takes them apart, right? So now instead of being tightly together and spinning very fast, things are taken apart. And so that causes all that cold air to then leave the Arctic and head southward. And that's going to cause this wavy jet stream that you see on the picture on the right. And so disruptions in the polar vortex are actually key indicators about how we can get extreme winter weather here in the mid latitudes. And that actually happened this past January. So on the right is an animation of the polar vortex from December into January, and you'll see this sort of milky white coherent structure that was spinning around in December starts to get sheared apart and torn apart into January. And that was actually our first indication that things were going to get a little bit rocky coming up into late January and early February. So how does this all work though, right? I talked about the Arctic warming up, but how is that really affecting the polar vortex? Well, this is a nice image from the National Science Foundation. And basically what happens is as you start to warm the Arctic, this means you can get more heat to enter into the polar stratosphere. So again, like I said, if you start to heat up the polar stratosphere, that cold air that was locked up is not as cold anymore. And so the vortex will start to not be as tightly wound as it was before. So as we start to warm the vortex, the westerlies will start to slow down. And once that starts to happen, then everything relaxes away and the jet stream becomes wavier, weakens, and these intrusions can start to happen because now you've allowed this slacking to happen. The jet stream can move downward and cold air can start invading the middle latitudes. So as the Arctic starts to warm, we might expect that this feature should start to increase with time, i.e. the polar vortex should start to weaken with time. And indeed, that is happening. So what I'm showing here is, again, it's a trend, so a change with time of the heat flux going into the stratosphere. So red colors here mean that since 1990, we've been adding more heat into the stratosphere at that location. Blue colors means that there's been less heat being added in the stratosphere. And I want to point out to this big red area that's occurring over Siberia. This is significant heating that's going into the polar vortex region from Siberia over the last 30 years. So we've been adding more heat into the polar stratosphere in this region. This also happens to be a hotspot region anyways, or a source region for heating for the stratosphere. So we have a favorable area that we're amplifying the heat on. So we're turning up the crank even more. That, as you might expect, should cause the polar vortex to start to weaken. And indeed, when we look at trends within the polar vortex itself, so this is, again, these are changes in the strength of the polar vortex. So here, red means the polar vortex is getting warmer, or the bowl is getting less shallow. So the heights, these are heights, so the bowl is getting less shallow. And so you can see that indeed right over the pole, the heights in the stratosphere are starting to increase, meaning that the vortex is weakening with time. So these things that we're now seeing, these are actually happening in observations. We're seeing these connections happening within the observations. We can also do some other things to take a look at the polar vortex. So again, on the left are two other measures of polar vortex. One, the top is where is the center of the vortex every season. So we go to every season since 1979, and we sort of calculate where's the average center of that vortex. And you can see that with time, the center of the vortex has been shifting southward, the average center. This means it's being pushed off the pole a lot more, i.e. it's weakening and moving into the middle latitudes, as we might expect. We're also seeing that the vortex size is also decreasing with time, and that's on the bottom plot in that brown line. And so again, what does this mean? This means the cold pool reservoir that was over the Arctic is getting smaller, i.e. it's being depleted, and more of it's getting moved out into the middle latitudes. So all of these pieces from the observations are all sort of pointing us towards the extreme winter weather that we've been experiencing lately. Yeah, that's probably been because the polar vortex has been a lot more disturbed over the last 30 years. And you can see it again if we look now at our mid-troposphere. So this is the layer where the weather's happening. If we look at changes that are happening here, you can see that over the northern, North America here, central North America, these blue areas means that we're getting more troughing, meaning colder air is coming down. You can also see it going into Asia and also into Europe. And so you can imagine that this is sort of showing you those meanders, because if you kind of follow along, you can see there's a big dip going on here. These reds are where it's going up. So the jet stream goes up over Alaska and then dives down across North America. And when that area dives down, that's what's going to help to bring the cold air southward. So in observations, we're actually seeing the pieces come together that are telling us that the polar vortex is actually getting more disturbed. That should be leading, from our theory, should be leading to the extreme winter weather, which is what we've been experiencing over the last 30 years. And if we look at the cold wave that happened just this past February, you can indeed see this is the circulation that was happening during the middle of that pattern. And you can see that it matches exactly what the trend is over North America. So if I flip back and forth, this big cold blob, that's that piece, that's that intrusion of that cold air that's come down. Here's that ridging over the Arctic that we're also seeing in the overall trend over the last 30 years. So this event that happened over the last month is really iconic of what the overall trends have been in our winter weather for the last 30 years. Okay, so let's all just try to put this together as I start to kind of wrap up here. So Arctic amplification is occurring. There's no question about that, okay? Our global climate change is happening. Arctic amplification is occurring. The polar vortex has weakened and it's shifting off the pole more with time. This more disturbed polar vortex is giving you these bigger meanders into the middle latitudes, and that's helping to induce the extreme winter weather over the last 30 years. So hopefully all of these things I've sort of laid out sort of these different pieces to help to guide you along here. So now, of course, the next conclusion that you might want to draw or would draw would be, okay, well, that must mean that Arctic amplification must be causing the recent extreme winters, i.e. climate change is responsible for the recent winters. Let's put a caution on that, okay? We're not going to put a wrong, we're not going to put a right, okay? We're not going to say that's the wrong conclusion, we're not going to say that's the right conclusion. As scientists, there's a lot of other possibilities. You know, you might have heard the phrase correlation is not causation. So you can have a whole string of things. We have a theory that these all pieces get together, but one of the other fundamental pieces of science is that we want to make sure that this is actually reproducible, meaning we would look at other data sets or other data to try to figure out if we can reproduce these same results or see if these results and hypotheses hold. And so actually, one way we could do that is actually take longer records of the polar vortex strength. And so that's what's shown here is a longer record of that polar vortex strength measure. So if the red line goes up, that means the polar vortex was weaker that year. We're going back now to 1900. Remember, we were stopping in about 1980, 1990 before. And if the line goes down, that's a measure that the polar vortex is getting stronger. And so you can see since 1900, there's not been actually a clear trend. This black line is sort of an average over time, about a 7-year average over time. And you can see that the polar vortex actually goes through cycles. And I've helped to highlight some of those cycles here for you. So you can see, for example, at the very beginning of the 20th century, the polar vortex was overall very strong, okay? Very low values of this index that we use to measure it. 1950s to the mid 1960s, it got weak, it got strong again in the 80s to the early to mid 90s. And then we've been seeing again, this recent change happening in the polar vortex over the last 30 years. So within this context, one thing that we could take away from this is that the weak vortex is not unique to the last 30 years. We've had other periods that have also featured a weak vortex, colder winters as well. So it's not quite unique in terms of that. In fact, other studies have also found this through some other records and proxy records looking back into the past, that really the vortex itself has what we call natural variability, meaning there's going to be times when it's going to be strong, and there's going to be times when it's going to be weak. And so the question is, over the last 30 years, do we just happen to be in a phase right now where things are overall weakened? So I think I'm almost about out of time. I want to make sure to get to people's questions. The other thing we can do as well is we can also look at climate models to try to see and try to reproduce this within climate models. The bottom line with climate models is, again, a big question mark. We get very mixed results. Some climate models simulate the link between Arctic amplification and the extreme winters and the meandering of the jet stream. Other ones do not. And in fact, some of the most recent evidence that has come out has actually been that in this recent paper by Russell Blackport and James Screen, that actually model experiments, when you sort of input Arctic amplification into the model, they do not reproduce this more waviness. And so their conclusions is that it might be that perhaps that's not the cause, that again, perhaps the jet stream itself also kind of has these natural cycles. So it's a little confusing, I will completely admit, but again, that's what makes science fun, is trying to disentangle everything. So here's what I can tell you. The recent wintertime trends in observed extreme weather, they are real and they're consistent with the Arctic amplification theory. But I can't tell you, at least to a scientific level, that they're caused by global climate change. Could be. Remember, we had the caution sign. We didn't put the X, we put the caution sign. Could be. The other thing is that also that this period of extreme winter weather, that actually there's some signs that we may be sort of coming out of it, and the next 10 to 15 years may be a little bit less extreme. Time will tell with that. But overall, winters will get warmer under climate change. And this is really important. Even the recent cold wave that we had in February here in the Southern Plains was still warmer than the winters. Overall, in terms of temperature, the overall winter was still warmer than winters during the late 19th and early 20th century. So the winters are getting warmer. There's no question about it. But there could be these periods where we're seeing these meanders within the jet stream caused by weakened polar vortex episodes. So I'm going to end it there. Here's some information about if you'd like to get a hold of me, email, my website, and also I'm also on Twitter if you'd like to follow me on there. And I'll leave it there and turn it over, and I'd love to discuss more with any questions on this topic.